Well, this is the third time I'm trying to record this video. The first time I said some stupid things, so I didn't post that on YouTube. The second time the batteries ran out, so I'm a little bit frustrated. I'm doing this the third time, so please, if I'm a little bit frustrated, please don't look at it as a bad way. Nothing personal against you. So the example says that we have 3-phase 230 volts, 27 kilovolt amperes, 0-point power factor load on the output, and it is supplied by 3 10 kilovolt amperes, I don't know, 1330 divided by 230 volts, 60 Hz transformers connected in Y delta by means of a common 3-phase feeder whose impedance is 0.003 plus J 0.050. So feeder is just a power line connected from the load to the transformer, and it has an impedance which is equivalent to this, but every phase has the same amount of impedance, and the loads are balanced, so it's gonna be easy to transform this from delta to Y, which I did in the 18th video. You need to watch that video first, so you can know how to do this particular example. The transformers are supplied from a 3-phase feeder whose impedance is this per phase. So the supply voltage from the power lines from the supply to transformers have also impedance whose value is this. So it has a resistive part and an inductive part. And the equivalent impedance of one transformer referred to the low voltage side is 0.12 plus J 0.25. So the transformer impedance, which I hope you know, those are the resistive impedance and the flux leakages in the transformers, but referred to the low voltage side is equal to this. Determine the required supply voltage in the load is 230 volts. Okay, so in order for us to do this particular example, we need to transform this delta into a Y connection. We did that in the 18th video, and then we are going to make a single phase equivalent circuit. So from a single phase transformer, we know what is the supplied voltage on the primary side. But first, in order for us, this here is a little problem, because when you transform a delta to a Y, its impedance also changes. So this is the impedance of the transformer per phase referred to the low voltage side. For us, it is better to refer it on the high voltage side, so we are gonna then we don't have to worry about transforming when we are transforming the delta to a Y connection, because we know what is the impedance of the transformer looking it from the high voltage side. So let's first this refer to the high voltage side. So if we want to do that, we first need to know what is the turns ratio. The turns ratio of this particular transformer we know by the rating voltages, which is equal to this. So let's leave it like this. Now, the equivalent impedance of a transformer from the high voltage side is equal to A squared times the impedance, 0.12 plus imaginary number times 0.25, and when you do this you get 4.01 plus J 8.36. I know it because I'm doing this the third time. Now the impedance from here, I'm gonna just follow me. I'm gonna draw a circuit, so don't panic about this if you don't understand. It will all be clear in a minute. So the impedance, we transfer it from here. Now we can connect this to a Y connection, not from a delta. We're gonna connect connect this to a star or a Y connection. But for that we have to know what is the now equivalent turns ratio for the YY, because YY turns ratio, because the you know, if when we saw that the voltages change if we connect this from the delta to Y in the previous videos. So the new turns ratio, if we connect this from a delta to a Y transformer, is equal to square root of 3 times it. We did this in the 18th video. So this is equal to square root times 1330 divided by 230, and this is equal to 10. I already know in advance. Now what have we done? Because we transferred this to a Y connection, we can now, we can now draw the single phase equivalent circuit. And I'm gonna do it like this. And now the single phase equivalent circuit looks like this. On the primary side, we have this feeder impedance. 0.8, that is the resistive part, and the inductive part is J.5. So this is from the primary side. We have this feeder over here. Now we referred from the low voltage side to the high voltage side, the transformer impedance, the resistive part, the windage losses, the windage resistances of the transformer per phase is equal to 4.101, and the reactive flux linkage reactance is 8.36. Now we can draw here some windings over here, and this is the supply voltage on the primary side, and this is the voltage V1 on the coil of the primary side of the transformer. On the secondary side, we have a feeder impedance, not on the load. This is a delta connection, but this is here on the line impedance, let's say. On the secondary side, it is 0.003. J 0.015. And there is a load connected with a voltage VL. Here we have V2, and there is a current that goes IL, current load. And the transformer ratio is 10 to 1. So we connected this to a Y, and now this is the schematic for one single phase. Okay, now let me see how much battery I have. Not too great. Okay, now we have to calculate what is the supply voltage over here. But we have an ideal transformer. We can now refer all this circuit to the low voltage side. So as we did with single phase transformers, this is now a single phase transformer theory. I hope you know that. And then we're going to calculate what is going to be Vs, because we now know everything, the impedance, all the resistances in the impedance when we refer it to the low voltage side. We can do it on the high voltage side, but this is easier on the low voltage side, because we know what is VL. I'm going to show you what is VL. And we know what is the current, because we have the apparent power over here. Over here, it's going to be easier for us to calculate it. And we can easily calculate what is the Vs. Refer to the low voltage side, and because we know the turns ratio, we can just bring it back into the original value. So first of all, what is the load voltage, do you think that the load voltage now is 230 volts? Think about it. What is the amount? Well, I'll give you 5 seconds or stop the video and just what is the load voltage on the output? It is not 230 volts. Why? Because in the original state this is a delta and we had a delta load. Okay, sorry, this is a bad, but this is a delta load. Now it said that the load the load is connected to 230 volts. So here you have 230 volts. But when we transfer this to a Y connection, and for this to be the same, then here the line and the phase voltages are the same. But in the star connection it is not. The phase voltage from here, the line voltage from here to here is 230 volts. But the phase voltage here is 230 divided by square root of 3. So this VL over here is not 230 volts. Because we transfer this from a delta to a Y connection, this will become 230 divided by square root of 3. Because it's now a star connection or a Y connection. So VL is now 230 divided by square root of 3, and that is equal to 133 volts, and let's say 0%, which means we are gonna refer all these values to the low voltage side. It's easy to do that. Now, this is the load in a star connection. That's why you have to be, when you transfer from a delta to Y to make it easier for computing and calculating, you have to do this. Okay, now, what is the current IL? Well, the parent power stays the same, and the parent formula for the parent power is equal to, for a Y connection, is equal to VL L I L. And sorry, the phase voltage times the phase current. I don't have time because of the battery. You can check this out on the internet. You have to know this before you start learning electrical machinery. So from here, the IL, which is the same as the phase voltage in a star connection, is equal to the apparent power divided by 3 times the phase voltage, which is equal now VL. This is not the line voltage, this is the load voltage. That is equal to 27,000 times 3 times 133. And that is equal to 76.76 amperes. Now, all these values I'm going to refer to the low voltage side, and I'm going to add that with this impedance, and then I'm going to calculate easily the VS. So the schematic looks something like this. Here we have VL. Here we have that VS applied, that is referred to the low voltage side. And here we have current IL with the phase angle 0.9. I don't know how much. power factor, but I'm gonna calculate this. So first we have to refer all these values to the low voltage side. This is resistance R and this is X, YX, JX, sorry. R, how do we calculate it? First we are gonna add 0.8 plus 4.01 because it is in a series. And if you refer it to the low voltage side, we have to divide it by A squared. A squared is 100. Plus the resistive impedance on the secondary, on the low voltage side is 0.03. That all will be equal to R. So the resistance over here is equal to 0.051 ohms. Refer to the low voltage side. X is equal to, we only have to reactance, we don't need to put a J, we'll do it later. So we add 5 and 8.36. Divided by A squared plus this impedance over here, X will be equal to 0.149. So R is 0.051 and here we have J 0.149. All we have to do is first calculate the phase angle over here. This is too much alcohol. I think I will be able to write down with a marker. Okay, now what is the power, the angle of the current? Well, we first, what is that phi angle? Well, if we know that the power factor is 0.9, then this is how can we measure what is the angle of the current, because this current has a real and a reactive part. That is equal to 25.8 degrees. So the current is IL, but minus 25.8. Why minus 25.8? Because it says it is lagging. Now we have VL, we have all this impedance, we know the current, and we can easily calculate VS. By second Kirchhoff's law, you get that the VS is equal to VL plus IL with minus 25.8 degrees times 0.051 plus J 0.149. VS is equal to, VS referred to the low voltage side is equal to 133 0 degrees, plus IL was 6, I unfortunately brushed it, was 67.67 minus 25, 8, 0.051 plus J 0.1. Now this is mathematics, I did it a lot of times in this course, and when you finish all this, you get that Vs is equal to 140.7 3.1 degrees volts. So this is the amplitude referred on the low voltage side. So this is the supply voltage referred to the low voltage side, and that is how much we have to give to the system, the supply, so that we will have 230 volts the output in a delta connection. So we just calculated what was the important part for us here was this. Now if you want to refer this on the if you want to give it to the origin, this is for the low voltage side. If you want to bring it back to the high voltage side, you just do this, A times Vs, but A prime, because this is a YY equivalent bank, and you get 10 times 140.7, and that is 1407 volts. So in order to supply this load with all of these specifications, we have to bring on the supply voltage this amount of volts on the supply. So this is the, I think, line. This is the necessary line-to-line voltage. No, this is the necessary supply phase voltage of the. Yes, this was the phase voltage because this was all YY bank, but the necessary line-to-line voltage from here to here. So this Vs is from here to here. Now, if you want V line-to-line, you just multiply this with square root of 3. And you get 2,437 volts. So this is the line-to-line voltage on the supply line. And I don't have much battery, and thank you for watching, and see you in my next video. Goodbye.